Hello everyone, my name is Leno from the Lawrence Livermore National Lab, and this is joint work with Rafael Cobb from the Advanced Institute for AI and Renato Vicente from Serasa Experian. So probably everyone here knows that if we train a model using a lot of data, this model will probably have a higher accuracy than if we train it using a low amount of data. The problem is that gathering data and building data sets is a very costly and a very hard process. And so the main idea of transfer learning is to leverage the data that we have from a given task to another task that is related but not equal, and then try to improve the accuracy of the model, even though we have less data for the new task that we call as target task. But this is a hard thing to do. And why is that? Well, first we have to define what is a task. Basically, the task is composed by a marginal probability distribution, which defines how likely a given observation is to be sampled, and the objective predictive function, which given a specific observation, what is the correct label for this observation. And the reason why it's hard to perform transfer learning is that when we change from one task to another, we might have covariate drift, which means that the sampling probabilities are different. For example, you can imagine if you are doing a survey about the Brazilian population, if you only interview people between 20 and 25 years old, you have a sampling problem compared your population with the whole Brazilian population. Or you might have concept drift, which basically means that given the same observation, the label might be different in those different tasks. So we propose two different scenarios in which you could do transfer learning. The first one we call as model refining, which basically means that you train a model using the data set from the source task, and then use the data that you have from the target task to refine this model. So change a little bit the model to be more specific for the target task, and then you have a refined model that hopefully is much better than if you have only used the small amount of data that you have for the target task. Another scenario is the model adapting scenario that should be used when you have data for the target task, but you don't have labels for it. And so what we do here is that we train a model using the source task, and then we build a new model based on how the observations change from the source to the target task, even though we don't have the labels for the target task. And the way we do that is by proposing a tree adaptation mechanism. And if you know how the decision trees work, basically you have nodes in the decision tree, and each node represents a test. And you're gonna walk through the decision tree until you find a leaf node, and then this leaf node will represent the label. And our idea is to refine this tree or change this tree model by recalculating the thresholds and pretty much change the tests and changing the way the decision tree splits the data according to the new task that we have at hand. And the way we do that, we recalculate the thresholds based on this metric that is shown here. So basically we maximize it. And what does this metric mean? So basically we are kind of like minimizing the divergence between the distribution of values assumed by the samples in the left subtree and in the right subtree before and after the test changes. So for example, in the first test, the tree will split the data in a given way. But since the distribution of values might have changed in the new task, you have an uneven split of the data, and we have to minimize the divergence between those splits. But as you can see in the equation, we need a specific distribution of values to apply in the equation. And these distributions change according to the scenario we want to use the algorithm. In the first one, in the model refining, the distribution is the distribution of labels. And in the model adapting scenario, since we don't have labels, we use the distribution of the attribute values itself. And for evaluating our approach, we consider two different domains. In the circle domain, we have to classify if a sample is inside or outside the circle, and the circle might change of radius, or we can change the way the observations are sampled from the circle. And in the mushroom domain, it's a real-world domain from the UCI database, in which you have to classify if a mushroom is edible or not. And we compare three different algorithms, let's say this way. The first one is you only using samples from the source task to train the model, only using samples from the target task, or using the struts approach that is our proposal here, that we refine or adapt the model. For all of them, we use tree gradient boosting as the base learning algorithm. So we can see the results here. Basically, in only one scenario, the only source algorithm was better, which was in the circle domain, probably because there was a very small difference between the source and target task. But in all other situations, our proposal presents a better performance, and it might be a very different one, especially if we compare in the mutual domain, that is the real world one. So we have some increasing performance in all other scenarios, which is a very positive outcome. So as a conclusion, we have proposed a tree-adaptation model in our paper, and we showed the variations of this model to situations in which you might have covariate or cross-surface drift, or both of them. And our experiments show that our method is useful. So I hope you will be able to find more details about it in our paper or in the poster session. Thank you.